Lab 5, Choose Your Own Adventure. The purpose of the lab was to observe the motion of a daredevil falling from a large distance and draw conclusions about his motion with our knowledge of physics as well as compare it to a theoretical model. The models and physics principles used in this lab are Newton's second law of motion and drag force. These are used to determine the net force acting on the body as well as calculate the motion with kinematic equations. The main result of our lab entails that our computational model has our daredevil reach the ground faster than expected. However, this can be explained. We use the momentum principle to derive the velocity update and position update formulas in the y direction. This will be used to explain the idea behind what is happening in our computational model, where gravity and drag are affecting the motion of the daredevil. Beneath here you can see our gradual progression from the momentum principle to our kinematic equations. And next we use net force with drag force during free fall to determine what our drag constant B is. So as you can see here, during free fall, the net force acting on the daredevil is 0. So we know that the weight of the daredevil is equal to the force of drag that he feels. The force of drag is equal to BV squared, where B is, as I said before, drag constant. And so isolating for it, we see that B is equal to mg divided by vt, which is terminal velocity, which is the max velocity that the daredevil reaches, squared. First step was finding exactly what the value of our drag constant B was equal to. So I did this I found the terminal velocity by using the website provided about Daredevil's flight, and his maximum vertical speed was 1,357.6 kilometers per hour. So converted over to meters per second, that is 377.11. And I found his mass on the internet as well. So I was able to determine that B is equal to 0.005031. And then I just had to transfer over all this information to my code. So I used the code from one of the previous labs. So you can just ignore where it says ball everywhere. So I entered the mass in his initial position vector from where he jumped out of, which was about 36,000 meters above the ground. And then next I entered what our value of B was. And then I had to calculate F net. So I did negative mg plus bv squared in the y direction, as you can see. And then I had to update the momentum principle with velocity and position update formulas. That's what those last two lines are right there. And then this yielded a position versus time graph and a velocity versus time graph, as you can see down here. And yeah. Did he break the speed barrier? Yes, in fact, according to our computational theoretical model, he far surpassed the speed required to break the sound barrier. But this is because our model does not account for a few things. For example, it does not account for the different densities of air at various altitudes, which would result in various drag constants at various altitudes, altering the force felt on the body. We also do not account for how temperature affects the system. Increased temperature would increase the velocity and frequency at which the air molecules collide with each other. This would increase the drag force, and as the daredevil continues to fall and the air around him increases in temperature due to the disturbance. Also, our model does not represent the part of the flight where the daredevil would pull his parachute. This would prolong the flight time, also making it more accurate.